How do you make an ester? Let's find out in this video. To make an ester, you can simply take a carboxylic acid, add in a lot of alcohol, and then add in a little bit of acid, heat it up, and you'd get an ester, usually within an hour. Let's see this reaction. So we have this carboxylic acid. I'm going to draw it quite big and use a red pen so that you can see the exchange or swapping of the OH group with the OH group of the alcohol. So reagents on top, any alcohol R represent a general group in organic chemistry, and in the presence of large amount or in excess of alcohol and with acid catalyst. What you get is, again, R, and then, so that maintains that oxygen, and now that oxygen is swapped or replaced with the oxygen from the alcohol. All right, and also don't forget, we have water as our living group. So that's how to make an ester. In FISCHER esterification, even though it looks to be a very simple reaction, the mechanism or how the ester is produced seems quite complex. Okay, let's go step by step on the mechanism, where I will just start with a simple acid. So this is, and again I'm going to just use the red pen to show that the oxygen is coming from the carboxylic acid. I'm going to have just a simple R1 to denote that the first R, this group, is actually coming from the carboxylic acid. And then for your information, this FISCHER reaction happens in equilibrium, meaning that if you add in a large amount of alcohol, it will start to hopefully push towards the right hand side of the equation. Therefore, you would hopefully push for the production of ester.
A few moments later.
Okay, and we just have a catalyst. So I'm going to draw a catalyst that we're going to use in this reaction is the sulfuric acid. So H2SO4. H2SO4. So we're going to actually in here since there are two lone pairs on the oxygen of the carboxylic acid, on the carbonyl of carboxylic acid, so it will then pick up the hydrogen from the sulfuric acid, and I'm going to draw it as so the carbonyl group here is being protonated by the hydrogen, and you have also that SO4 minus going around. Okay, and that's the all right. So now when it's already picked up a proton or hydrogen, it'll be positively charged. Okay, so now is ready to be attacked by the alcohol, because here in this point, this carbon becomes more electrophilic. All right, and now is amenable, is easily attacked by an alcohol. So if I have R O H, and on the oxygen there are two lone pairs, that lone pair can then attack the carbon there, which is an electrophile, and then this goes in there. Okay. And the next thing is, again, the equilibrium. It's in equilibrium, and what happens is that once it's attacked there, it will open up. So we're going to draw the it's open up. So from a double bond to a single bond, and now we have the OH group. Let me open it up again. All right. So when it attacks the carbon of the carbonyl, in other words, it will make a new bond. So now a new bond with a have H there, then your R. I'm going to label that as R2 to make it different from the R1, from the carboxylic acid. Okay, so now since it has 3 bonds, the oxygen of the alcohol would have a positive charge. Okay, so now it's time for this group, one of these OH group, to leave, from the carboxylic acid whole framework. This proton can be picked up by, if there is an OH going around, so that can pick up this proton and that neutralize the charge on the oxygen. And then what happens is that you can have, let me just draw the equilibrium first. Okay, so one of these will leave as a leaving group. So say we take the top one. So this still have the 2 lone pair, and that can go and pick up, say, a proton from D here. So we can actually just go pick up a proton, and that will be like that. Okay, so that can also go on and be, become the one that can pick up that proton as well. In other words, this is proton transfer. Yeah. Okay, so once we have this, the next thing is that if we do this, let's just draw this again. So this is now a good leaving group. Okay, so how could they leave? Okay, so what we do now is we're going to, since this has 2 lone pair, what happens is that this electron can then flow into the bond to form the carbonyl again, and then this bond will be broken. All right, and the next thing is, let me just shift it away a bit, and let's do that. Okay, so R1 again, R1, but now I'm going to shift it to the top here. So this carbonyl, this newly formed carbonyl head, I will shift it back to the top, because to replace this one. So I'm going to just use this one and then shift it to the top. So that's the carbon. That's again, remember the oxygen here. So this oxygen remains, is still coming from the carboxylic acid, and that still have the hydrogen there. You still have that single lone pair and is positively charged at the moment. That's already left, yeah. So I'm gonna just leave it as, put it this way, H2O as a good leaving group, and then this oxygen will shift it on the side. So it will, this oxygen is coming from the alcohol, R2. Okay, so we pretty much have back something similar. If you look at this one, this is very similar to this species. You see, I'm gonna just draw a dot there to show these are similar to the other one. Okay, so we are actually returning in one full circle. If you're aware of it, going back to this same species more or less. You still have the carbonyl, you still have the positive charge, the same goes with this carbonyl, positive charge, and still, in other words, protonated. So this comes back into the picture. Not as H2, HSO4 minus. So since that, you can actually then pick up the hydrogen, and that goes into it. Goes into it to neutralize the charge, more or less. And then at the end, what we have is we have, so I'm going to draw again the R1. Okay, we take a look. So you just compare these two, where we start with carboxylic acid. Now we also end with the same species, but now instead of the red oxygen, yeah, OH, we have the blue, which is coming from the alcohol, and we have the R2 instead of the OH group. And we also have the catalyst, sulfuric acid, regenerated. I'm going to shorten this esterification. First is make sure the alcohol is in excess, a lot of alcohol. Second is to make sure to use an acid as a catalyst, So normally we have sulfuric acid or toxic acid, and it'll be, as you remember, one of the main feature of a catalyst that is being used in the reaction, and then it'll get regenerated at the end of the reaction, and it helps in terms of making the reaction smoother, faster, reduces the activation energy of a reaction, especially in the case that if you have only, for example, you only have the carboxylic acid with alcohol, the reaction will be very sluggish. It's gonna be very, very slow reaction. So when the carbonyl picked up the proton here, what happens is that it gets activated. This part of the molecule, the carbonyl, especially the carbon now, is more electrophilic. Therefore, it gets, in other words, activated. It allows an attack from a nucleophile. Yeah. So in this case, the nucleophile is the alcohol having the two lone pairs. can attack, and that will opens up the structure. And then here is when one of the OH group in the carboxylic acid has to leave. So you can choose one of them. So again, in this case, the one that helps in making OH group a good leaving group is again a hydrogen. So when one of the OH group in the carboxylic acid gets protonated, it becomes a good leaving group, that is water. So that can leave and form back the same species. Yeah, this protonated carbonyl group is, you see this a lot in the carbonyl chemistry. Alright, so that's the end of this classic reaction, Fischer esterification. And if you have any question or you'd like to know more about this, please put in your comments in the comment section. And I hope to see you in the next video.